Okay, you may now begin.
Okay, so we chose to do problem 2, which is phone a friend. And as you can see, here's us with our, imaginary telephone cups. And so in this experiment, we're basically going to talk about and explore how the quality of sound changes based on different factors. And the factor that we chose to change in our experiment was the tension in the rope. And yeah, we'll continue to talk about that. So of course, we need to define in our case what quality means. And we did something really similar to one of the groups that went previously. And that's we took 2 quality parameters. One of them is that how much noise there is. So when you put in a pure tone, it only has one, sound, one frequency in the noise. But then when it comes out the other side, it can be distorted or have different noise that comes out the other end. So we want to say that the less noise there is, the better quality the sound will be. And then our second parameter for quality is just how loud it is, depending how loud the sound that we receive is. And we didn't vary the sound loudness of our input. So we can assume that, from the output, from the data we got, we can compare those directly. So in this experiment, we basically, as I said earlier, we took our variable to be the tension in the rope, and we measured the slack length of the rope, and then we set tensions under that length and then over that length. So we took ones that were like a really slack rope and then a really tight rope. So we wanted to see how that affected the sound quality that came out. And so we made a hypothesis, and we basically said that the quality will increase as the tension in the spring increases, and that would be especially visible when going between, changing from below slack length to above slack length, because if you just think about it, right, something that is stretched tightly is able to oscillate well or better, I guess, but then something that's slack, right, it's hard for it to oscillate. It will just kind of be slack. And if you connect this to, the physics aspect, we can consider this as Q, which is the quality factor of an oscillator, and it's defined to be the average energy stored in the oscillator divided by the average energy that's dissipated over 1 radian of motion. And so this basically means you can think of it as, over time, how well does this oscillator keep oscillating? And the higher the Q, the higher the quality, right? So, and just as another point, our hypothesis and our project was based on the idea that the system is a force-damped oscillator. So in this case, the sound wave that we put through the system is our driving oscillation, or our driving force in some sense. And then there's damping in the system as well due to, internal damping of the string, etc. And in this experiment, we didn't vary the type of string at all. So that was kept constant, and therefore we could make good comparison. But yeah, if we had more time, we probably should also explore, different string types with different internal dampening amounts. Okay. So in this case, we just listed our materials. You can read through it, but it's just basically how to make a basic setup for our project. And in this picture, you can see generally what we did. And so the string between 2 yogurt cans, I guess. And then we also had a little bit of sound dampening on the input side, just to make sure that there was as little leakage of noise from, not through the wire, but just through the outside air. So we put a cap on the input side of the audio, and we also put Ananda's jacket over it. So, hopefully that helped. And then on the right side, you can see our microphone sticking out the end. And then this is basically how our setup looked like. And you can see in this case, we took 4 different measurements, and our string slack length was 27.5 inches. So we took 27 inches, and then we went up 28, 29, and 30. So here's just a rundown of the methods as I explained. So we basically took the sound, or we recorded the sound using PY audio, and then recorded the 441 hertz from my phone, which is on the left side, using a website that outputted just 441 hertz. And then we recorded the audio using PY audio and a microphone on the other side. And yeah.
So this is a graph of what the audio looked like in Python. So if anybody's interested, we used the wave package in Python to get out the data from the .wav file. And then this is basically what the output was. And then we put this in the Fourier transform, and Python we used the fast Fourier transform just for efficiency. And we did that with the SciPy package. And on the next slide is what we got out as our outputs. So this is 27, 28, 29, and 30 inches. And our expected input Fourier transform was just at 440 hertz. There'd just be one frequency because that's what we put in. We couldn't actually measure it because we didn't have another microphone. So it's just a lack of equipment, but we just took this to be our hypothetical input. And so as we can see here, 27 was below the slack length. Oh yeah, and all of this data has been normalized just so we can see the noise a bit clearer. So for 27, you can see that the noise is very, very high. And that's because this is below the slack length. And once we go to 28 inches, which is above the 27.5 slack length, the noise decreases by a lot. And then, the noise slowly decreases, but not at the rate that it went from 27 to 28. But we can see clearly that there's a correlation between the amount of stretch in the string and then the amount of noise that we get out. And then on the next part, we looked at the peaks. So now we can see the peaks, and here's a table of all of them. They're increasing slowly, but it's important to realize that this is like a harmonic oscillator with forced oscillations. And so these peaks won't go up forever. In fact, when the peaks will be the greatest when the natural frequency of the string is close to the natural frequency of when the forced oscillations of the 441 hertz is close to the natural frequency of the spring. That's when the amplitude is going to be the most. So it will continue rising until it hits that point, and then it's going to start decreasing.
Unfortunately, your time is up.
Okay. Yeah.
Were you close to the end?
Yeah, that's fine.
Yeah,
we just had some error discussion, but we covered the bulk of our presentation.
Okay, cool.